You are made of dead stars. That's not a metaphor. That's chemistry. Every atom in your body was forged inside a star that exploded before the sun even existed. You are literally, physically, cosmically recycled. And somehow, that's not even the wildest thing we're going to cover today. We are diving straight into the deep end of that cosmic madness. So subscribe now to make sure you never miss a journey like this. Trust me, the things we are about to uncover are absolutely worth staying for. Okay, let's go back. Way back. Before stars. Before planets. Before atoms. Before literally anything. 13.8 billion years ago, everything, and I mean everything, was squeezed into a space smaller than a proton. Not a small room. Not a tiny planet. Smaller. Then, a proton. And then it exploded. But not like a bomb exploding into an empty room. Or like the room itself started growing. Space wasn't expanding into something. Space was the something that expanded. That distinction is going to mess with you if you sit with it too long. So let's keep moving. This event is called the Big Bang, and here's what's wild about it. We have no idea what caused it. We haven't figured it out yet. We physically cannot use our laws of physics to describe what happened before it. The math breaks. Like divides by zero, crashes, give up and go home breaks. The universe before the Big Bang is not a mystery we're solving. It might be a question that doesn't have an answer in any language we're capable of inventing. But here's the thing. About 1 microsecond after the Big Bang, things get weird in a very specific way. The universe is a soup. Not metaphorically. It's a hot, dense, insane plasma soup of particles and energy. There are no atoms yet. No hydrogen. No anything recognizable. Just quarks and gluons smashing around at temperatures so high that if you tried to write the number out with zeros, you'd run out of arm before you finished. Then the universe starts cooling. And cooling. Slowly. Over hundreds of thousands of years, the temperature drops enough for electrons to stop fighting against protons and just stick. Hydrogen atoms form. The first atoms in existence. And then something incredible happens that you could actually see if you were there. The universe, which was opaque, like trying to see through a wall of fire, suddenly becomes transparent. Light travels freely for the first time. That light is still traveling right now. We call it the cosmic microwave background, and we can literally detect it with a radio telescope. Your old TV with the static channel? N. A tiny fraction of that static was from the afterglow of the Big Bang. You've been watching the birth of the universe, and you just called it bad reception. Now we've got hydrogen. Mostly hydrogen. Some helium. A tiny sprinkle of lithium. That's the entire periodic table at this point. 3 elements. The universe is, cosmically speaking, an underachiever. So how do you get from hydrogen gas floating in empty space to, say, a planet with oceans and dinosaurs and teenagers arguing on Reddit? And this is where gravity walks in and saves the story. Gravity is patient. Unbelievably patient. Over millions of years, tiny random differences in the density of that hydrogen gas, like one region having just barely more atoms per cubic light year than another, start pulling. Gravity makes dense regions denser, which makes them pull harder, which makes them denser. It's a feedback loop, and it ends in one of the most violent events the universe produces. A star is born. Here's how to feel what that's like on a human scale. Imagine you're squeezing a stress ball. The harder you squeeze, the hotter it gets. Now imagine squeezing it so hard that the atoms inside start fusing together. That's nuclear fusion. That's a star. A star is just gravity squeezing hydrogen so hard that hydrogen atoms slam into each other and become helium, and that collision releases an absolutely absurd amount of energy as light and heat. Wah! The sun converts 4 million tons of mass into pure energy every single second. 4 million tons per second. And it's been doing that for 4.5 billion years. And it's not even halfway done. Stars are not candles. Stars are the most powerful sustained explosions in the known universe. But here's where the story turns. Stars don't live forever. And the way they die depends entirely on how massive they are. And this is where the universe stops being just big and starts being genuinely dramatic. A star like our sun has a lifespan of about 10 billion years. It lives, it burns hydrogen, it runs low, it puffs up into a red giant, basically a star going through its dramatic final era, and then it collapses into a white dwarf. A white dwarf is roughly the size of Earth, but has the mass of the sun. Wah! A teaspoon of white dwarf material would weigh about 15 tons. Not because of any exotic physics. Just because that much mass is crammed into that tiny a space. Density is wild like that. The sun will eventually become a glowing ember the size of a continent, slowly fading over trillions of years, till it's a cold, dark rock drifting through space. That's a humble ending for something that made all life on Earth possible. But not every star gets a humble ending. Some stars are massive, like 8 to 100 times the mass of the sun massive. And those stars live fast, burn out young, and go out like they have something to prove. When a massive star runs out of fuel, gravity wins instantly. The core collapses in less than a second. Less. Then a second. And the outer layers, which were just sitting there doing their thing, suddenly have no support and come crashing inward, and then bounce. That bounce sends a shockwave outward at a significant fraction of the speed of light. This is a supernova. It's brighter than an entire galaxy for a few weeks. Wah! One exploding star outshines 100 billion other stars combined. And this is not a rare thing. Supernovae happen in the Milky Way roughly every 50 years. We just haven't seen one up close lately, because most of our galaxy is blocked by dust. We're overdue. Now, here's your awe moment. Sit with this one. Every element heavier than iron in the universe was made inside a dying star, or in the chaos of a supernova explosion. Oxygen. Carbon. Calcium. Iron itself. Gold. The iron in your blood, the stuff that makes it red, was made in the nuclear furnace of a star that exploded before our solar system existed. You are not just made of star stuff, in a poetic way. The calcium in your bones was forged in stellar nucleosynthesis. The oxygen in your lungs was cooked up in a star's core over millions of years. You are a temporary arrangement of atoms that have been through multiple stellar deaths. You are the universe looking at itself. That's not a metaphor. That's nuclear astrophysics. Okay, back to the drama. When a truly massive star collapses, and I'm talking 20 or more solar masses, the core doesn't stop at a white dwarf. The gravity is so intense it keeps going, crushing protons and electrons together into neutrons, and you get a neutron star. A neutron star is roughly the size of a city, like Manhattan. But it has more mass than the sun. Why? The surface gravity is so strong that if you dropped a marshmallow onto a neutron star from 1 meter above the surface, it would hit with the energy of an atomic bomb. A marshmallow. From 1 meter. We need to keep moving, but just let that one breathe for a second. Some neutron stars spin hundreds of times per second and shoot beams of radio waves from their poles like cosmic lighthouses. We call those pulsars. When astronomers first detected them in 1967, they literally labeled the signal LGM-1, little green men, because the signal was so regular and precise that for a brief moment, the possibility of alien origin was on the table. It was a spinning dead star, but for a minute, it was aliens. Science is fun. Now, what happens if the collapsing star is even more massive? And what if gravity doesn't stop at neutrons? What if nothing stops it? You get a black hole. A black hole is a region of space where gravity is so extreme that not even light can escape. And this is where most explanations go wrong. Because they make it sound like a black hole is a vacuum cleaner sucking everything in. It's not. A black hole just sits there. If you replace the sun with a black hole of equal mass, Earth's orbit would not change at all. We'd just be very cold and very dead, but not because of the black hole specifically. Black holes don't suck. They just have gravity. Like everything else. They're only dangerous if you get very, very close. But here's the thing about the boundary of a black hole: the event horizon. Cross it, and you can't come back. Not because something grabs you. Because every path forward in space also leads inward. The geometry of space-time itself points toward the center. You're not being pulled. You're falling through a universe that has run out of directions pointing away. That's not poetic license. That's general relativity. And right at the center, the math breaks again. Same as the Big Bang. We get a singularity, a point of infinite density, and our equations just scream and crash. We genuinely do not know what's actually there. Black holes are the universe's way of putting a do not enter sign on the most interesting rooms. So we've got stars forming, living, dying, leaving behind white dwarfs, neutron stars, and black holes. Gravity pulling gas into galaxies. Galaxies colliding and merging over billions of years. The Milky Way has somewhere between 200 and 400 billion stars in it. 400 billion. And the observable universe has somewhere around 2 trillion galaxies. Do the math and try not to have a small breakdown. Wah! That's more stars than grains of sand on every beach on Earth. By a lot. But here's where the story takes a turn that nobody expected. Not even the scientists who discovered it. In 1998, 2 separate teams of astronomers were doing routine measurements of distant supernovae, trying to figure out how fast the universe was expanding. Everyone assumed gravity was slowing the expansion down. That's what gravity does. The question was just how much. But the data came back wrong. The supernovae were farther away than they should have been. The universe wasn't slowing down. It was speeding up. The expansion of the universe is accelerating. Something is pushing space apart faster and faster over time, and we have absolutely no idea what it is. We call it dark energy, because giving something a name is how scientists cope with not understanding it. Dark energy makes up roughly 68% of the entire universe. More than 2/3 of everything that exists is this stuff we cannot detect, cannot measure directly, cannot explain, and cannot agree on theoretically. It just shows up in the math as a term that makes the equations work. And dark matter? That's a whole other mystery running in parallel. 27% of the universe is dark matter, stuff that doesn't emit light, doesn't reflect light, doesn't interact with light at all, but has gravity. We know it exists because galaxies spin wrong without it. If galaxies only had the visible matter we can see, they'd fly apart. The outer stars rotate too fast. Something is holding them together, and it's invisible. We've never directly detected a dark matter particle. We've built the most sensitive detectors on the planet, buried them in mines to block interference, and waited years. Nothing. Dark matter refuses to introduce itself. So to recap the universe's composition, 5% is normal stuff: atoms, stars, planets, you, coffee, everything you've ever interacted with. 27% is invisible matter we can't detect. 68% is a mysterious energy accelerating the expansion of space. We understand 5% of the universe. 5. That's not a gap in knowledge. That's almost complete ignorance, which is actually incredibly exciting if you think about it, right? Now let's talk about quasars, because they are insane and don't get enough screen time. A quasar is what you get when a supermassive black hole, we're talking billions of solar masses, is actively feeding. As gas and matter spiral into the black hole, they form an accretion disk that heats up to millions of degrees and blasts out jets of energy from the poles. Wah. A single quasar can outshine an entire galaxy by a factor of 1,000. One object, brighter than 1 trillion stars combined. The most distant quasars we've observed are so far away that their light left before Earth existed. We're not looking at them now. We're looking at them 13 billion years ago. Telescopes are time machines. Every image of a distant galaxy is a fossil of the early universe. The Hubble Space Telescope, the James Webb Space Telescope, these aren't just cameras pointed at pretty things. They're letting us watch the universe's childhood in real time. Webb has captured galaxies forming just a few 100 million years after the Big Bang. Galaxies that look like they shouldn't exist yet, according to our models. The universe is already breaking our best theories, and we're barely getting started. So where does this all end? The current leading model is called the heat death of the universe. Over incomprehensibly vast timescales, we're talking numbers with so many zeros that scientific notation feels inadequate. The accelerating expansion spreads everything out. Stars burn out. Black holes evaporate through a process called Hawking radiation. Yes, black holes eventually evaporate, slowly bleeding energy as quantum particles, over timescales longer than the current age of the universe raised to the power of itself. Eventually there is nothing left but cold, diffuse photons spreading through an infinite, dark, empty space. No heat gradients. No energy differences. No structures. No information exchange. Just nothing happening, forever. And here's where we zoom back out to the beginning. You are made of dead stars. That's still true. It's always been true. Every atom in your body was born in a stellar furnace, scattered by a supernova, drifted through space for millions of years, clumped into a solar system, cooked into a planet, stirred into chemistry, and eventually arranged itself into something that can watch YouTube videos and feel things about it. The universe spent 13.8 billion years building the conditions for you to exist for maybe 80 years, and then disperse back into the cosmos. You are an incredibly brief, incredibly improbable arrangement of ancient stellar debris that somehow became conscious enough to be curious about where it came from. And here's the question nobody has answered yet. If the universe began in a state of near-perfect uniformity, just hydrogen gas, nearly identical in every direction, then how did the tiny quantum fluctuations that seeded every galaxy, every star, every planet, ever you actually arise? Are they random? And? Are they the echo of something that happened before the Big Bang in some deeper structure of reality we can't access? Did our universe bubble out of another? N. Is there a multiverse? And are the rules of physics different elsewhere? And would a universe with slightly different constants produce anything at all? N. We don't know. That's not a failure. That's an invitation. If everything we are and everything we build will eventually dissolve into a cold, dark, endless nothingness, does our brief flash of consciousness actually have a purpose? Or is the universe just playing a cosmic joke? Then, drop your answers in the comments below, and subscribe if you haven't already.